Question 1, Chapter 2, Exercise 2.4. In the exercise, we need to find the matrix produced AB and BA. First, we calculate AB. For matrix multiplication, we multiply each row of matrix A by each column of matrix B. For example, the element in the first row and first column is 3 times 1 plus negative 2 times 0 plus negative 1 times negative 3. Then this gives us 6. Repeating the same process for all entries, we obtain AB equals this one. And next, we calculate BA using the same method and using the same process. And the answer is BA. This is the answer. And since AB is not equal to BA, we calculate that matrix multiplication is general, not communicated. Question 2, Chapter 5, Exercise 1. In this exercise, we are asked to find the dot product U.V and V.U. The dot product is calculated by multiplying corresponding components and then adding them together. So 2 times 3 plus negative 5 times 2 plus negative 1 times negative 3. This equals 6 minus 10 plus 3, which is negative. Therefore, U dot V equals negative 1. Now we calculate V dot U. This result is also negative 1. Thus, U dot V equals V dot U. This shows that the dot product satisfies the communicate property. Question 3, Chapter 4, Exercises 1. This exercise asks whether the statements are true or false. Statement 1. A vector space can only be made of vectors. This satisfies is false. A vector space may also consist of matrix, polynomials, or functions. Statement 2. A space must satisfy closure to be a vector space. This statement is true. A vector space must satisfy closure under addition and scalar multiplication. Statement 3. The set containing only the zero vector is a vector space. This statement is true. The zero vector remains in the set under addition and scalar multiplication. Therefore, the set contain only the zero vector is a vector space. Question 4, Chapter 4, Exercise 14. In this exercise, we are asked to find a spanning set for a neural space of matrix A. First, I swap row 1 and row 2 because row 2 contains the leading one. Next, I eliminate the entry below the pivot in column 1. Then I interchange row 2 and row 3 to obtain a pivot of 1 in column 3. After that, I eliminate the entry below pivot. Finally, I eliminate the entry above the pivot in column 3. Therefore, the reduced row entry form is this one. From the ref, we got the equation x1 equal to x2 plus x4 minus 3 x5 and x3 equal negative 2 x4 plus 2 x5. The three variables are x2, x4, x5. Let x2 equal x, x4 equals t, and x5 equal r. And then substituting this parameter gives. Therefore, the spanning set for neural space is this one. And the final neural span is 2, 1, 0, 1, 0, minus negative 2, 1, 0, negative 3, 0, 2, 0, 1. Question 5, Chapter 4, Exercise 25. In this exercise, we need to determine whether the given matrix forms a basis for R2 by 2. The dimension of R2 by 2 is 4 because there are 4 independent entries. Each matrix in the problem contains a 1 in exactly one position and 0 elsewhere. Any matrix can be written as A, B, C, D, and AE1 plus BE2 plus CE3 plus DE4. Then we use A, B, C, D to calculate. Then we got A, B, C, D. Then therefore, this matrix spans the entry space, and they are also literally independent. Hence, the given matrix forms a basis for R2 by 2. So yes, there are a basis of R2 by 2. Question 6, Chapter 4, Exercise 27. In this exercise, we need to find the rank of matrix A, a basis for the continuum space, and the dimension of the continuum space. And first, we perform Gaussian elimination. The matrix is A, and using the first row as the pivot row, we eliminate the entry below the pivot. For row 2, we subtract 2 times row 1. And this gives 0, 0, 0. And the matrix becomes this 1, 3, 10, 0, 0, 0, 0, 0, 0. And we observe that there is only one pivot, therefore pivot is only 1. Then rank A equals 1. The pivot column is the first column. According to the theory, the basis for the continuum space is obtained from the pivot column of the original matrix. Therefore, the basis for the continuum space is 1, 2, 3. The basis A called A is 1, 2, 3. Final, the dimension of the continuum space equals the number of basis vectors, since there is only one basis vector. Therefore, the rank is 1. And the basis contains the first continuum vector and the dimension is 1. So the answer is dim con A equals to 1. And these are all 3 answers.